We're surrounded by this invisible force that powers pretty much our entire world. I mean, it's in your phone, your toaster, the lights above your head, everywhere. But what is electricity, really? Well, in this explainer, we're going to demystify that invisible force and break down exactly how it works. Nice and simple.
I mean, think about it. You flip a switch and boom, light instantly fills the room. It feels kind of like magic, right? But what's really going on inside those wires? Well, we're about to pull back the curtain on that so-called magic, and I'm going to show you how it all works using one really, really simple analogy. Okay, so first things first, what actually makes electricity move? Because it doesn't just flow all on its own. Imagine water sitting in a perfectly flat pipe. It's not going anywhere, right? It needs a push to get it going. Well, it's the exact same idea for electricity. It needs a push, and we call that push electric pressure. All right, so let's stick with this water idea. Imagine electricity is just water flowing through pipes. In this setup, a battery, that's kind of like a big water tower. It's up high, creating pressure. That pressure is what we call voltage. And the water actually flowing through the pipe, that's the electric current. And what if the pipe gets really narrow and squeezes the flow? Well, that's resistance. Seriously, this simple analogy is the key to understanding pretty much everything else we're going to talk about. So this push we've been talking about, it has a formal kind of sciencey name, potential difference. But you and I, we probably just know it as voltage. It's that electrical pressure coming from a source, like a battery, that gets everything moving. And it's simple, really. Higher voltage just means a bigger push. Okay, so we've got the push. Now what? Well, once you have that push, the charges start to move. And that flow, that is the absolute essence of electricity. So let's take a look at that next. Right, so this flow is called electric current. Let's go back to our water analogy for a sec. If voltage is the pressure pushing the water, then current is how much water is flowing past a certain point every single second. See, it's not just that it's flowing, it's the rate of flow that's super important here. And we measure this current in something called an ampere, or just amp for short. Now get this, just one single amp is the equivalent of about 6 quintillion electrons flowing past a single point every single second. I mean, that is a truly staggering number of tiny, tiny particles all moving together. All right, so we've got the push, that's voltage, and we've got the flow, that's current. But there is one more crucial piece to this puzzle. Because not all paths are created equal, right? Some materials let electricity just zip right through, no problem. Others, they put up a fight. And that fight is exactly what we call resistance.
Yeah, you can think of resistance as basically electrical friction. A copper wire, that's like a big, wide open pipe, super low resistance. But the plastic coating around that wire, that's like a solid brick wall, incredibly high resistance. So it's the material itself that determines how much it's going to slow down that flow.
Okay, so now we've got our 3 key players on the field, right? We've got the push, the flow, and the squeeze. Voltage, current, and resistance. So the big question is, how do they all work together? How are they all related? Well, it turns out their relationship is actually incredibly simple, almost elegant.
And here it is. This is Ohm's law. It's this beautiful, simple formula that just ties everything together perfectly. The push, or voltage, equals the flow, or current, multiplied by the squeeze, or resistance. Think about it. If you want more flow, what do? You either need a bigger push, or you need less squeeze. It's really that simple. And this little equation, it's the foundation of pretty much all circuit analysis.
All right, Now that we understand the fundamental law of the game, we can start looking at the two basic ways you can actually wire things up. And I mean everything, from those cheap holiday lights to the entire electrical system in your house. It's all based on one of these two setups, series and parallel. So, here's the difference in a nutshell. A series circuit, everything is on one single loop. Think of it like a one-way street. But a parallel circuit, the current gets multiple paths, multiple branches to choose from, kind of like a multi-lane highway. And believe me, this one little difference has some major consequences.
So with a series circuit, the electricity has to go through every single component one after the other. You know exactly what this is like if you've ever had those old-fashioned holiday lights. One bulb burns out and the entire string goes dark. Ugh, the path is broken, nothing works. Yeah, not exactly ideal, is it?
Parallel circuits, on the other hand, are way more flexible. Each device gets its own separate branch. So if one light bulb in your living room burns out, the rest of them stay on, no problem. And this is exactly why your house is wired in parallel. It means you can turn on your TV without also having to turn on the toaster at the same time. Pretty useful, right? Okay, so we know how to get electrons moving, and we know how to control their path with series and parallel circuits. But how do we actually turn that flow into something useful? You know, like heat for our stove or light for our rooms. Let's dive into that. Remember that electrical friction we talked about, resistance? Well, just like when you rub your hands together to warm them up, forcing all those electrons through a resistor creates heat. This is called Joule's law of heating. And what's cool is that it's not some annoying side effect. It's not a bug, it's a feature. In a lot of our devices, that heat is exactly what we're trying to create.
And this is where choosing the right material is so important. For a good heating element, you need two things. You need really high resistance to generate a lot of heat, and you need it to get super hot without, melting or burning up. That's why special alloys like nichrome are perfect for this job. They're literally designed to get hot and stay hot, powering all sorts of things we use every single day.
So that brings up a question. How do we measure how quickly a device uses up all this energy? Well, there's a name for that. It's called electric power, and we measure it in watts. A 100-watt light bulb is just converting electrical energy into light and heat much faster than, say, a little 10-watt bulb. So yeah, power is all about the rate of energy use.
And this finally brings us to something we can all relate to, your electricity bill. And here's the key thing to realize. You don't actually pay for watts. That's just power. You pay for kilowatt hours. And a kilowatt hour is a unit of total energy, not power. It's the total amount of energy you've used over a period of time. Like if you run a 1,000-watt space heater for 1 full hour, you've used 1 kilowatt hour. So let me leave you with this final thought, which I think is pretty cool. The electric company, they don't actually send you a box of electrons every month. I mean, the electrons are already there, just sitting inside the wires of your house. What you're actually paying for is the energy, the push to get those electrons that are already there moving and doing useful work for you. It's a really subtle but pretty powerful shift in how you think about this invisible force that powers, well, everything in our lives.